here's the question that I asked at the end of the previous part of this video lecture. And the way to decide this is to use symmetry. It's going to be easier if I label these charges, so let me call them 1 and 2. And because they're positive charges, we know the E field at any location points away from each of them. So we have 2 contributions to the field at P, one due to charge 1 and one due to charge 2. And to get the total field, we need to add those. Symmetry tells us that those have identical horizontal components, and their vertical components are the same size but opposite sign. And so when we add them together, the vertical components are going to cancel out, and we'll get a field directly to the right. And so the answer is C. One thing to keep in mind about electric fields is that they're an abstraction, and much of the time what we really want is the forces. But the point of the field is that it often gives us a quick way to find the forces that we need. So suppose that we already know the E field at some location P. Maybe we've previously measured it with some probe charge, or maybe we know enough about all the source charges that we were able to find the field at P. It doesn't matter, we know the field at P somehow. Then in this case, it's easy to find the force on any charge that we place at the location P. And again, it just comes from this definition of the E field. Note that it's related to a force on a charge divided by that charge. And that charge is just some charge that has been placed at the point P, which we normally call a probe charge, but we don't need to call it that. But that means that the force on any charge that we place at P, it can be obtained just by rearranging that. We just multiply the charge by the field. So think about what that means. If we put any positive charge at point P, then we're multiplying that E field vector by a positive scalar, and we'll get a force in the same direction as the E field. On the other hand, if we put a negative charge at point P, now we're going to be multiplying that field vector by a negative scalar, and so we get a force on this charge which points opposite to the direction of the E field. If you carry out the sort of process that I've just carried out at many points for this pair of charges, you would get something that looks like this. And you can get quite practiced. You just sort of quickly imagine what the 2 E fields at a point due to the 2 charges would look like, and you vectorially add them. And you can fairly quickly draw a diagram like this once you're practiced. But there's a different type of diagram that we often draw, which is quicker to draw and sort of gives the overall shape of the field a little more of a quick visual summary. And it's a field line diagram. And the idea is you draw some lines, they have to come out of positive charges, and they have to go into negative charges, and the number you draw in or out is proportional to the charge. So I'm just going to say, 1Q means 8 lines, and so I'm going to have 8 lines in or out of each of these. If I had a charge 2Q sitting around here, it would need 16. And I just made up that number 8, but it tends to result in pretty good diagrams. And so now lines start on the positive charges and end on the negative charges, and you have to indicate which way that line is going. This is going this way. And this one would have to come down like this. And these would arch way out and come back in. And this, if you look along here, the field is straight up everywhere here, straight up everywhere here. And so these lines, this one leaves and this one comes in. And the field is tangent to these lines everywhere you've drawn a line. And the other thing is that where the lines are packed close together, like they are here, the field is stronger. A very common situation, because it comes up in a lot of technological applications, is the electric field due to parallel plates with charge on them. And what you usually have is two plates, perhaps they're made of copper or some other metal, and they're charged so that one is positive and the other is negative, and they have the same magnitudes of charge on them. And one example is something called a parallel plate capacitor, and that's what we're going to call these all the time, although technically a lot of these devices are not really capacitors. And this distance in between the plates, it's important for the approximations we're going to use to talk about fields in between here, that this distance between the plates is small compared to the dimensions of the plates. So whatever this length, say, is of the sides of the plates, that has to be much bigger than d. Also, it doesn't matter what shape these plates are. They could be squares, they could be rectangles, they could be circles, or any other shape, as long as you have two parallel sheets with charge on them. And then, as it always does, the field will have to point from the positive plate to the negative plate. Now, if you look at a capacitor, here's a pretty typical capacitor. If you open up a piece of electronics, you'll find lots of things that look like this. And the way the plates are arranged may not be like you would think. If you unwrap it, you find this piece all rolled up in here. And in fact, what it is the two plates that are parallel, but then they sandwich this thing called a dielectric, and one thing that does is hold them apart, and the other thing it does, well, is complicated, and we won't get into it. But it holds the two plates apart, and then it's rolled up, so it doesn't really end up looking like this. But there are other devices where you really do have two big plates parallel to each other, not rolled up. We won't typically draw a parallel plate capacitor this way. That's rather bothersome to draw. We'll usually draw a simplified side view like this. But when you see this, you have to remember that these are plates. This is a three-dimensional thing, and so these are going into and out of the page. And now look at the field. I've drawn field lines, and I've drawn them all parallel, and it turns out that's how it looks. The E field between the plates is uniform and the same magnitude everywhere and perpendicular to the plates. You can show that with some difficulty. If you think of a point in here and just think of adding up all of the fields due to all of the charges on the plates, you can wave a calculus magic wand and show this, that the E field between the plates is the same everywhere, except out at the edges where it bends out a little bit and is weaker. But we're going to approximate that that isn't so and that it's just uniform. And it turns out this is the value of the magnitude of the E field in there. That Q is this charge on the plates, that A is the area of the plates, and this epsilon naught is a physical constant we haven't met before. But there it is, and it turns out to be closely related to Coulomb's constant K, which is right here.
In writing down the E field inside a parallel plate capacitor, I used a meaning of the charge Q. The symbol Q in that E field equation has a very particular meaning. So suppose we have parallel plates, and this capacitor has a charge Q of 1 nanocoulomb on its plates. Which of these pictures is what we mean by that sentence?